Every scientific discipline has its holy grail, and the holy grail of physics is definitely quantum gravity. Quantum gravity is Einstein's unfinished revolution, the missing unification of general relativity and quantum theory. String theory is the best-known contender, and this week we have a strong newcomer. You see, the issue is that Einstein's theory of general relativity doesn't have quantum properties. So if we take a particle and do an experiment that tests its quantum properties, like the famous double-slit experiment, then we don't know what happens with its gravitational field. The quantum particle goes both ways at once, so you'd think the gravitational field of the particle also goes both ways. But that can't be, because Einstein's theory doesn't have quantum properties. Most physicists think that the solution to this problem is to give quantum properties to space and time. This is what happens in string theory and in loop quantum gravity and in asymptotically safe gravity and in almost all existing approaches to quantum gravity. But this new approach works entirely differently. The idea that was pioneered by Jonathan Oppenheim is that space-time and with that gravity remains a non-quantum theory, or a classical theory as physicists say. Oppenheim has been working on this for a long time, and now he's published 2 papers at once. In one single-authored new paper, he spells out the general mathematics for the idea. He says that leaving space-time classical only works if it fluctuates randomly, because that'll make it compatible with quantum mechanics. Models in which space-time remains classical will generally increase some measurement uncertainties, and this one does too. This might sound counterintuitive. Why does removing quantum properties increase uncertainty? But think of it this way. If you have a particle that goes 2 paths at the same time, and the gravitational field does that too, then the gravitational pull always points to the middle. If the gravitational field is not quantum, then it goes either left or right, but not both, so it must fluctuate between the two. So, more uncertainty. In a second paper, Oppenheim, together with several colleagues, works out a way to test the idea. They say the best way to test it would be to very precisely track the mass of some weights, because that should slightly fluctuate. This test might become possible in tabletop experiments in the near future. Tabletop experiments are what physicists call an experiment that doesn't cost billions of dollars, like, particle colliders. Another interesting thing about this idea is that it has a collapse of the wave function built in, so the measurement problem of quantum mechanics disappears. This fits together very nicely with the idea of Roger Penrose that gravity is what causes the collapse of the wave function. But Oppenheim's work is a mathematically more complete treatment, and indeed, I find it quite impressive. It'll take me some time to fully digest the paper, so let me just say, this is a very strong contender that I think can plausibly claim to solve the problem. However, there are always multiple ways to solve mathematical inconsistencies, like that between general relativity and quantum mechanics, and this is only one of them. So in the end, experiment must decide. I wonder what Einstein would have said about this. Hello? Hi, Albert. Yes, I'm afraid that means that God is still playing dice. Oh, I didn't know that craps is a dice game. That explains a lot. Well, thanks for calling in. Bye. This is the maybe most surprising development in theoretical physics I've seen for a decade or so. A well-renowned physicist is saying that there's a mistake in a proof that dates back half a century, and black holes might not actually contain singularities. The physicist in question is Roy Kerr, who's famous for his contributions to general relativity. He was the first to understand how to mathematically describe rotating black holes in Einstein's theory. Prior to this, physicists only knew how to describe black holes that sit still. But in reality, when you have matter that undergoes gravitational collapse, it'll generically have some angular momentum, and that angular momentum is conserved. So the final black hole must be spinning. If you want to describe real black holes, therefore, you need the mass to describe their rotation. And that's what Kerr managed to do. These rotating black holes are therefore also known as Kerr black holes. Black holes are characterized by their horizon, which is the surface of a region that you can only get in, but not out. I just explained in a recent episode on time travel that Kerr black holes are incredibly weird because they have two horizons, and it seems that between them you can actually go back in time. Whether that's really possible or not, no one knows, but it shows that we don't really understand these solutions. Besides the horizon, black holes all have singularities inside, or so we thought. The singularity is a place where the curvature of space-time becomes technically infinitely large. With this, tidal forces become infinitely large, so everything will be ripped apart as it approaches the singularity. The horizon itself does not have a singularity. Now, in the early days of general relativity, some physicists said that black holes are mathematical artifacts. They can't exist in reality. Then Stephen Hawking and Roger Penrose said, no, it's the other way round. When matter collapses, it's impossible to prevent black holes from forming, and they all must have a singularity inside. These are the famous Hawking-Penrose singularity theorems. They should have both won a Nobel Prize for it. Unfortunately, Hawking died before that. Penrose got the Nobel Prize in 2020. Kerr now says there's a mistake in that proof. His argument is roughly the following. Hawking and Penrose used an argument about the length of curves. They basically said in a black hole space-time there are curves which have finite length, and the only way this can happen is if there's a point where they end, which is the singularity. The problem is that the length of a curve is usually related to the time that passes on the curve, which is called the proper time. But for light, no time passes. So for the curves on which light moves, you need to measure the length in some other way. You do this by what's called an affine parameter. If you don't know exactly what that is, don't worry. Relevant is just that the affine parameter isn't the same as time. So why worry if it ends? Kerr now says that the Hawking-Penrose proof draws wrong conclusions from this affine parameter. If the affine parameter ends, that doesn't mean that the curves end at any finite time, because those are two different things. In the example he gives, the affine parameter is an exponential function of time. This will be bounded from below, so it kinda ends, but the curve still continues for all times, so no singularity. In his paper, Kerr doesn't mince words. He writes, "Why do so many believe that the star inside must become singular at this moment? Faith, not science. 60 years without proof, but they believe." It seems to me that Kerr's argument is almost certainly mathematically correct, and it's to the shame of many theoretical physicists, including myself, not even a particularly difficult argument. The question is then what this physically means. There are three things that came to my mind immediately. First, just because the proof that black holes contain singularities isn't correct doesn't mean that the conclusion isn't correct. It might be that this distinction which Kerr pointed out actually tells us something about the type of singularity rather than about whether they're present or absent, and someone else will complete the proof. The second thing to know is that there are other reasons physicists think black holes give rise to singularities, which are more on the physical side. Most importantly, if you compress matter beyond a certain critical density, we don't know any force that could create enough pressure to stop it from completely collapsing. And we have numerical simulations for that, though of course those never really create singularities because that'd blow up even the best computer. The third thing to know is that most physicists don't think there's a singularity inside black holes in any case. It's because near the singularity they expect the quantum effects of space-time to become important, but we don't have a theory for that. Though maybe now we do, if you remember yesterday's episode. What's new about Kerr's argument is that he says you don't need those quantum space-time effects to get rid of singularities. Little Albert is mightily impressed by this paper and also slightly amused that so many physicists could have been so wrong for so long. Today I have some really bad news, so grab a cup of tea or maybe scotch. Ready? A new study says that climate change will make big parts of the world uninhabitable much faster than expected. And I think they're making a very good point. Have you ever wondered why, if our body temperature is about 37 degrees Celsius, do we not find that same temperature comfortable as room temperature? It's because to work properly, the human body needs to cool. We constantly produce energy to power our muscles and brain. Well, at least some of us do. This energy production generates heat. This keeps the body at the right temperature, but it's actually too much heat, so we need to get rid of it constantly. This is why a comfortable air temperature for humans is well below body temperature. It's so we can get rid of this excess heat. If we can't get rid of this excess heat, it'll build up and within a few hours lead to organ failure and death. How well we can get rid of this excess heat depends both on the temperature and the humidity of the air. The higher the humidity, the less we can cool by sweating. Meteorologists measure this by what's called the wet bulb temperature. This wet bulb temperature is measured by covering the thermometer in a water-soaked cloth. If the air is dry, the cloth will cool the thermometer because the water evaporates and that carries away energy. The water-soaked cloth simulates sweating, basically. The limit of survivability for humans is usually said to be a wet bulb temperature of 35 degrees Celsius. At this temperature, humans can survive up to 6 hours. The authors of the new paper now say that in reality, trouble starts at far lower wet bulb temperatures. The authors say that the assumptions for this threshold temperature are unrealistic, because these assumptions are that people are indoors or shaded, naked, completely sedentary, fully used to the local heat, and are neither over nor underweight. I don't know about you, but I don't spend my summer sitting naked indoors, so I think they're making a good point. Then they went and calculated new thresholds for wet bulb temperatures for diverse people under realistic circumstances. Old people, overweight people, people with clothing who still want to go outside. There are a lot of numbers in this paper, so I'll just give you some examples. People aged 18 through 40 can survive those 6 hours indoors at temperatures up to 34.1 degrees of that wet bulb temperature. And for those aged 65 and up, it's 33.7 in the best case. If they still want to go outdoors, that threshold drops further. Now, those 1.3 degrees might not sound like much of a difference, but if global average temperatures continue to rise, this threshold will be crossed more frequently much earlier. The impact will be felt particularly hard in India, Saudi Arabia and Central Africa, where we might soon see large numbers of people die from heat stroke. Yes, we'll all die sooner or later, but some ways to die are more pleasant than others, and overheating isn't one of them. Just ask my old Honda that sadly died on the way from Arizona to California. Well, we'll all die, except of course Brian Johnson, because plasma facials are going to keep him young forever, I'm sure. Last week, Virgin Atlantic chartered the world's first ever transatlantic flight powered by sustainable aviation fuel. Their Boeing 787 flight from London to New York was powered by a mix of waste oil and biofuel and was intended to test their performance. Sustainable aviation fuels, SAF for short, are a catch-all phrase for several different types of fuels. What they have in common is that they chemically resemble kerosene, but that they cause much lower carbon dioxide emissions than the usual stuff that's derived from fossil fuels. Sustainable fuels include synthetic fuels that can be created from renewable energy. They also include biofuels that are created from plants. These plants take carbon dioxide out of the air when they grow, so when you burn the stuff, that doesn't increase the amount of carbon in the atmosphere. And since airplane engines aren't known to be picky eaters, you can feed them with used oil. For example, the stuff that your French fries have bathed in. Airlines and the Biden administration are pushing SAFs as the most feasible way to decarbonize aviation, but the idea has some problems. First and most importantly, there isn't remotely enough of the stuff. Last year, the US produced just about 16 million gallons of it, which is less than 0.1% of the consumption by US airlines. Then there's the land use. One of Virgin's main SAF suppliers is the American company Virent. Their biofuel is made from corn sugars, wood and agricultural waste, but growing this stuff competes with land use for food supply. Since there's only so much waste oil and the land use of biofuels is high, to me synthetic kerosene seems the most viable option. It has the added benefit that since it's chemically extremely pure, it basically doesn't create contrails, which some climate scientists think contribute to global warming. Again, though, the issue is that there isn't remotely enough of it. Synthetic fuel production from renewables, sometimes called power to liquid, is a great idea in principle, but in practice it so far only exists in small trials. Either way, the US seems dead set on investing in the technology, with the Biden administration calling for SAF production to hit 3 billion gallons by 2030. Though I really think they're missing a major marketing scheme. Save the world by eating more fries! The brick is a boxy cloud of opaque dust at the center of the Milky Way, which has confused scientists ever since its discovery 30 years ago. It just got even weirder. Astrophysicists originally thought that the brick was just full of dense gases, which would absorb light. But then it should also have been full of young stars born from this dense gas. Yet those are nowhere to be seen. In reality, the brick is closer to a nunnery than a maternity ward. According to the new paper by an international team of astronomers now, the brick is full of ice crystals made of carbon monoxide. Carbon monoxide is one of the gases coming out of car exhaust pipes. You normally don't see it as ice though, or if you do, maybe you accidentally drove to Saturn, because the freezing point of carbon monoxide is minus 205 degrees Celsius. And that's the stuff that researchers say is in the brick. They figured this out with Webb's infrared telescope. They used this to measure how much of the light that came from the other side of the brick was filtered out by it. From this, they learned it contained significant amounts of this carbon monoxide ice. This is extremely weird, because according to our current models of galaxy formation, such a cloud just shouldn't be there. No one has any idea at the moment how it got there or what it's doing there. It's very confusing. It's also very interesting, because astrophysicists are still trying to understand the distribution and structure of matter in galactic centers, which is super important for the debate of whether dark matter or modified gravity is correct. Though I think it's just a huge traffic jam and it's exhaust fumes from alien spacecraft. IBM just announced they produced the first quantum processor with more than 1,000 qubits. And I got a lot of questions about what this means, so let's have a look. Last week, IBM revealed the IBM contender processor, which has 1,121 qubits. This is up from 433 qubits in the previously largest chip, and in line with the quantum roadmap that IBM has set for itself. Qubits are the operating units of quantum computers. If you manage to entangle them, you can use them to perform certain calculations dramatically faster than on conventional computers. However, the number of qubits in and of itself isn't all that relevant. You see, the type of qubit that IBM is using is tiny superconducting circuits. They're etched on silicon wafers similarly to normal microprocessors. Lumping many of them together isn't really the problem. I mean, not like I can do it, but IBM has been doing stuff like this for decades. No, the question is whether you can actually operate all these qubits as desired. In particular, you want to know how faithfully they perform operations and how large the error rate is. IBM hasn't released data on that, other than somewhat vaguely saying the new processor has a similar performance as the previous quantum processor with 433 qubits. Indeed, it's odd how little IBM has been saying about either this new chip or the previous one. They've preferred talking about an older, even smaller chip with just a little more than 100 qubits. This is even odder if you take into account that in 2018, people from IBM argued that the the number of qubits is not a good measure of performance and introduced a better measure called the quantum volume that'd be more suitable. But now they seem to not want to use this measure. Their quantum volume updates end in 2022 with a chip that has merely 16 qubits. So what can you do with this new 1000 plus qubit chip? No one really knows. But we do know that realistically, for commercially interesting applications, we'll need at least 1 million well-working qubits, so the quantum revolution will have to wait a little bit longer. According to researchers from University College London, the number of people identifying as transgender in the United Kingdom has steeply risen in the past 2 decades. The study just published in the British Medical Journal examined data from more than 600 primary care practices in the UK, covering over 7 million people aged 10 and up. Of those 7 million, about 2,500 had diagnostic codes indicating that they told their doctor about their trans identity. A little more than half of them had undergone some form of masculinizing or feminizing treatment. The data revealed that in the years from 2000 to 2018, the rates of people who revealed their trans identity to their doctor increased a lot. In 2000, on average, 1.5 in 100,000 identified as transgender. By 2018, this number was almost 5 times higher. The increase is particularly pronounced among young people. Since more people disclose their trans identity, the total numbers on record have also steeply risen, especially among young people. It's highest in the age group of 16 to 17 years, where now about 16 of 10,000 are on record as being trans. Strangely enough, the researchers also found that transgender identity was almost twice as common among those with lower socioeconomic status. However, they say that this might be an artifact of the data sample, which comes from primary care practices. These with higher socioeconomic status might prefer seeking private care and therefore have incomplete records. According to my recent study, 100% of people were born at birth, though it's yet to pass peer review and you never know. How much do you remember from this week's science news? Take our quiz to find out. Thanks for listening. We'll be back next week.